So starting in this video, we're going to move full-fledged into inferential statistics. And we're going to do that first by studying confidence intervals. So this chapter is going to be dedicated to confidence intervals. And we're going to find confidence intervals of two types. We're going to find confidence intervals for the population proportion, and we're going to find confidence intervals for the population mean. So let's first of all think about what a confidence interval actually is. So suppose a politician's approval rating is 49% with a 3% margin of error. What does this mean? So when political polls are done, such as like the president's approval rating and so forth, typically those are done using samples. So a sample of individuals are taken, usually around maybe 1,000 individuals are sampled. Usually those would be likely voters or registered voters. And anyway, a sample of, say, 1,000 individuals would be taken, and the proportion would be found in that sample that approve of the politician's performance. But because we're using a sample instead of a census, there's room for error. We've seen previously that samples vary. We've studied in the previous chapter how the sampling distribution of X bar, how the samples vary depending on which particular sample we obtain, and the same for the sampling distribution of P hat. The sample statistics vary depending on which particular sample we happen to randomly obtain. So the same kind of thing happens here. When we do a politician's approval rating, in this particular case, this means that there was a sample taken, and in that random sample, 49% of those selected approved of the politician's performance. But there is a 3% margin of error. So what exactly does that mean? Well, it means that, again, this is a sample, so the true parameter is most likely going to be within 3% of this sample statistic. So if we were to take, say, the 49% and subtract the 3%, and if we were to take the 49% and add the 3%, well, 49 minus 3 is 46, so that would be 46, and 49 plus 3 is 52, so 52%. What this would be saying is that the true approval rating for this politician is probably something between 46% and 52%. Again, we had a specific sample that said it was 49%, but because samples could vary, most likely the true proportion that approve of the politician's performance is probably somewhere between 46% and 52%. So that's the idea of what we're talking about with the confidence interval. So the confidence interval would be saying that the true approval rating is probably somewhere between 46% and 52%. Now, I've been emphasizing the word probably because there's a chance that the true approval rating is not within that margin. So we'll be talking about something called the level of confidence that we will tie with that, because there is a chance that we could be wrong even with this margin of error. Anyway, this is the kind of thing that we're going to be looking at in this particular chapter. And so let's begin. So when we want to find a confidence interval, we begin by finding a point estimate. So let's define a point estimate. A point estimate is the value of a statistic that estimates the value of a parameter. So depending on the particular statistical measure that we are discussing, then we're going to use the corresponding statistic as the estimate for the parameter. So for example, if we're wanting to estimate a mean, so if we want to know what is the population mean, then the statistic that we would use as the estimate would be the corresponding statistic. So X bar would be the statistic that we would use as the point estimate of the parameter, of the mean. Likewise, if we're going to estimate a population proportion P, then we would do that with a sample proportion P hat. So this is the statistic that we would use as the point estimate for this parameter. And these are the two that we're going to do in this course, but we could do this for any parameter. So for example, if we wanted to estimate a population standard deviation, then we would use the sample standard deviation as the point estimate, and so on. So for every kind of a statistical calculation that we've done so far in this course, we've had both a parameter and a corresponding statistic. And so again, we're going to use the statistic as the point estimate of the parameter. Some more definitions. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. In other words, what we're going to do, as I sort of noted with our beginning example of the politician's approval rating, we're going to have a point estimate, we're going to have a margin of error, and so we're going to use that point estimate with the margin of error to get our confidence interval. Now, the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted by a sort of a strange notation here, but it'll make sense as we move forward. 1 minus alpha times 100%. So typically, the most common level of confidence that's used in most statistical work is 95% confidence. So what that means is that the statistical techniques that we use to find the confidence interval means that 95% of the time we're going to obtain an interval that actually contains the parameter that we are looking for. So if we're doing 95% confidence, then 95% of the time using our statistical techniques, the interval that we end up with will actually capture the true parameter within that interval. But 5% of the time then, the confidence interval that we obtain would not capture the true parameter within that confidence interval. So let me give an illustration of this. Suppose the proportion of success in a population is P equals 0.7. So in other words, the probability of success is 70%. The following figure consists of 200 confidence intervals obtained from this population using a 95% level of confidence. So this vertical line that you see here is representing the true parameter, the 0.7. So this is the true parameter. And so from this population, if we were to take 200 different samples, randomly selected samples, and if we were to calculate the point estimate p hat and use that to calculate a confidence interval, then each one of these horizontal lines is representing a confidence interval. So for example, if you look at this first line here, it goes from about here to about here. The second line goes almost the exact same thing, from about here to about here. The third line goes from here to here, and so on. So again, if we are finding a confidence interval, each one of these horizontal lines is representing a confidence interval. So all of these lines that you see that are green are confidence intervals that actually contained the 0.7 within the confidence interval that was found. The ones that are red did not contain 0.7 within that confidence interval. So if you look, we have 200 different samples that were simulated here, and of those 200, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them did not contain the parameter. If 10 of them did not contain the parameter, then that means 190 of them did. And if we take 190 and divide that by 200, that is 0.95 or 95%. And that's the idea of a 95% level of confidence. Again, our statistical methods, if we're using 95% confidence, our statistical methods 95% of the time are going to give us an interval that actually contains the parameter that we're looking for. So that's the idea of the level of confidence. Now, I've mentioned that the most common level of confidence that's used in statistical work is the 95% level of confidence. But we could use any level of confidence that we want. So we might use 98% level of confidence. So if we use a 98% level of confidence, then that would mean that 98% of the time our statistical methods would give us an interval that contains the true parameter. We could do 90% confidence. Again, that would mean that 90% of the time our methods would give us an interval that contains the true parameter. So why wouldn't we just always use, say, a 98 or a 99% level of confidence? Well, there's a trade-off that we're going to see. As we raise the level of confidence, you're going to see there's a trade-off for that. And so there's reasons why that we maybe would stick with the 95% instead of a higher level. The truth is, though, we could use any level of confidence that we want. Again, most common's 95% level of confidence, but we could use 90% level of confidence, and so that's done. We could use 98, 99% level of confidence, and that's done. We don't usually go below 90% level of confidence, but we could, at least theoretically. And we could use 50% confidence if we wanted to, but the point of that is, I mean, what good is it? If we're only 50% confident that the interval actually contains the parameter, well, what good is that? Well, it's really not much good. And so again, normally we're going to use 90% confidence or 95% confidence or 98 or 99% confidence. And again, the most common is 95% level of confidence. So again, it's important for you to understand what that level of confidence means, and so that's why I'm kind of harping on that a little bit here. So again, our statistical methods, whatever our level of confidence is, which generically we're going to call 1 minus alpha times 100% confidence. So that's generically going to be our level of confidence. To be totally honest, I'm not crazy about that notation, so a lot of times I'll use the letter C. So I'll say we're C confident. So C is standing for confidence. So that would represent my 95% or my 90% or whatever. So again, if I'm using a C% level of confidence, then C% of the time, my statistical methods are going to give me an interval that actually contains the parameter. But then, of course, that means that, 100 minus C% of the time would be giving me an interval that doesn't contain the parameter. Another important thing to consider, whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. So that sample statistic is going to be a specific value depending on the specific sample that we obtain. And so that in and of itself is going to determine really whether or not the confidence interval will contain the parameter. Any sample statistic that is in the tails of the sampling distribution will result in a confidence interval that does not include the population parameter. So again, what I really want to make sure that you understand is the population parameter does not vary. The population parameter is what it is, but our confidence intervals are going to vary depending on the specific statistic that we end up with. So the parameter doesn't vary, but our confidence interval is going to vary depending on the statistic. And that is the point. Depending on our point estimate, that's going to determine whether or not the confidence interval will contain the parameter. Interpretation of a confidence interval. A 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from a population whose parameter is unknown will result in an interval that contains the parameter. So this is what we were discussing on the previous pages. Again, our statistical methods are going to ensure us that 1 minus alpha times 100% of all confidence intervals that we find will contain the population parameter. This is based on the law of large numbers. So the next question then is, how do we go about finding a confidence interval? And so we're going to pick up there on the next video.